So chapter 6 picks up from where we left off from chapter 5 with multiple degrees of freedom, but this time we look at what happens when you force one of the masses, or all of the masses in fact, of that 3 degree or n degree of freedom system problem. Okay, and we're going to go through a process known as modal analysis. Okay, and I'll talk about why we have to use that in a second. But so a little introduction. Talk about some of the theory behind modal analysis. So the properties, modal matrix and scaling. Okay, and then the forced response of an undamped multiple degree of freedom system. And the theory can be quite not challenging, but sometimes it's a little bit sort of, it's not very clear. It's a bit opaque in terms of how it applies. But the best way, obviously, is to go through some examples, and you'll see the process. But basically, it's a step-by-step process. There's a procedure that you should follow, and once you've got that procedure down, you can generally go about solving these problems. Okay. So there's a couple of worked examples that we'll go through, and then I'll talk about when you've got damping. And then if you've got a chance at the end of the lecture, I might do another example, but if not, we can leave that till the tutorials to do an example. I mean, there's already 2 worked examples in here, so I'll go through them certainly, but we might have a go at one of the exercises at the end if we've got time. Okay, so a multiple degree of freedom system is a system with inertia and compliance, okay, that can move in more than one way. Up till chapter 4, that was all single degree of freedom system, so it could only move in one way. But last week we introduced multiple degrees of freedom, reviewing what you'd covered last year. Okay. Now, many systems can be well described as what's known as lump mass. Okay. If you've got a very multiple degree of freedom system model, okay, but you're only interested in a certain aspect of it, you can actually lump all the masses together, assume it's a lump mass, and then you can deal with a smaller number of degrees of freedom. So an example would be something like a car engine. There's many degrees of freedom in the way it can vibrate and stuff. But if you assume the engine block and its cylinders and stuff is one mass, and you're only looking at vibration and perhaps a couple of degrees of freedom, then obviously you can lump that mass together, and then you can look at those frequencies. They're all going to be relatively low frequencies, so you can focus on them. But obviously, in certain situations, it may no longer be valid to treat the system as a rigid body. So with that car engine example, if you're looking at higher frequencies, so things like the position of the cylinders and the crankshaft and stuff come into play, you have to assume more degrees of freedom. Okay, and so you need to consider them, and that will bring in additional modes of vibration and additional resonant frequencies that you have to determine. Okay, and so up to now, we've dealt quite simply with 2 degrees of freedom system and 3 degrees of freedom system, which is, and the reason we've done that is it's relatively straightforward to follow the process by hand. But this method that I'm going to introduce will allow us to deal with much higher degrees of freedom, will allow us to deal with much higher degrees of freedom. But in fact, you'd actually get the computer to do this process with much higher degrees of freedom, because there's still a bit of labour involved in going through this process. But the principle still applies, and I'll show you that later on with another MATLAB model. So, modal analysis. This is where the theory starts. As we know, undamped vibration can be represented in matrix form like this. Okay, so this represents an n degree of freedom system. Okay, you've got your mass matrix, which you fill up. Okay, you've got your acceleration, and there's your stiffness matrix times by your displacement. Okay, and that equals 0. That's undamped free oscillation of a multiple degree of freedom system. Okay, so there's no forcing function, and that's the equation. And if you make that substitution, as we did in the lecture, you end up with what's known as the eigenvalue problem, where the goal of this problem is to find out what omega squared is. Okay, that's the goal of the problem. You know what k is, you know what m is. X is simply your displacement, and omega squared is what you're trying to work out, and those will be your natural frequencies, your resonant frequencies of the system, of the vibration. For force system, okay, you replace the 0 at the end of that equation with this thing, I've called it, for the sake of argument, P, okay, the applied force. however you want to call it. Now, for multiple degrees of freedom, when you go through and solve this, this is the main problem with the method that we've used before, is that all the equations are coupled together, okay? If you remember your stiffness, this wasn't, they are not coupled. You're just dealing with x1 double dot, x2 double dot, x3 double dot, and so on, because this is a diagonal matrix. All the other terms are 0. This is not a diagonal matrix. It's a symmetric matrix, but it's not diagonal. The terms off the diagonal have values, okay? And so basically, if you've got x1, 2, 3, and so on in this vector, okay, you're going to end up with a series of equations that both contain x1 and x2 and x3 and so on, okay? So you need to, the equations that you come up with, okay, for the individual masses, you're going to have mx1 double dot equals a whole bunch of stuff, okay? And that whole bunch of stuff is going to include the motion of x1, the motion of x2, because they're all linked together, okay? Now obviously, 2 degrees of freedom system, we can more or less do by hand. 3 degrees of freedom system, to do it by hand, you need to make sure it's a semi-definite system, because your equation becomes a cubic. Okay, so we can solve the cubic if it's semi-definite, because it ends up being a squared term times by a quadratic. That's fine. You get beyond 3, and it's much more difficult. You end up with a equation to the power of 4, an equation to the power of 5, and so on, depending on the number of degrees of freedom system you've got. And you can't solve them by hand. Okay, you've got to go through and solve, use them. You either use a computer or use this method to solve that. They're coupled. So the process, okay, we uncouple the equation of motion to give a set of individual second order ordinary differential equations, okay? Don't be scared, it's fine, because we've done a bunch of solving of this already. And basically, we end up uncoupling the equations of motion, okay? You solve each equation, which we can do, okay, because we've done that. Chapter 3 was basically solving an ODE. And then you combine the individual solutions to get the response of the system. But what we do is, in this first process, the way to uncouple it is we essentially replace x with what's called a modal variable, okay, which I'm going to call q. And there's a relationship between x and q that we'll see in the moment. You solve it in terms of q, and then you put it back into x, essentially, with what's going on. Now, modal vectors, this is where it gets quite opaque. I apologise, but I guess we should go through the theory. If we take our eigenvalue problem and rearrange it, okay, so that's where we had k minus omega squared m times by x equals 0. Okay, if we rearrange it so that the k and the m are on the other sides, and so we end up with this equation for a specific mode r. Okay, just called it mode r. Could be mode 1, could be mode 2, whatever. R is arbitrary. Now, if we pre-multiply, okay, by the transpose of a different mode, we get this. Okay, so here I've got mode s. Okay, and I've transposed it, which is what the t indicates, and I've pre-multiplied those things by that. I can't put this in because you can't multiply a matrix times a vector times a vector. You've got to have a transpose of the vector times by the matrix times by the vector. Okay, due to the way that matrices and vectors play with each other, you can't put them in any other way. So I've pre-multiplied by matrix by vector s, a different mode, transposed. So that's what I've done. And I could similarly have started with the s mode, where this is s, and pre-multiplied by r. So I get the same thing. Okay, instead of omega s, I've got instead of omega r, I've got omega s down here, and I've just done the same thing. It doesn't really matter. Now, because K and M are symmetric matrices, you can say that S and R can be interchanged with each other. So here I've got the K matrix, I've got the transpose of mode R, okay, times by K times by the mode S, is equal to the transpose of mode S times by K times by the mode R. Okay, you can say that that's the case. And the same can be said about the mass matrix. So that if I go back to this equation, this and this are actually equal to each other, okay? And this are equal to each other, okay? Because M and K are symmetric, you can say that that's the case. And obviously, if they're equal to each other, you can subtract one from the other. There's my two equations. Okay, so we can see based upon this, we can see that these two are equal to each other, and based upon this, we can see that these two are equal to each other. If I subtract one equation from the other, assuming that omega r and omega s are not 0, then we can say that this must therefore be 0. One mode transposed times by the mass matrix times by another mode will equal 0. Okay, assuming that those two omegas are not the same. But if you have the case where omega r and omega s are not 0, okay, sorry, are the same, okay, for r equals s, then you end up with this case, and that will end up not being 0. And that term, mr, is a single value, okay? If you take a 3 by 1 vector mode shape, okay, multiplied by a 3 by 3 times by a 3 by 1 vector transposed, you end up getting a single value, okay? And that is called the modal mass. So it's not a mass in terms of kilogram, it's called a modal mass because it's involved in the modal equations, which we'll go through and solve. So it's, you can't, we treat it like a mass, but it's not a real mass. And you do the same thing with the K matrix, the stiffness matrix. So you take the same mode, transpose it, times by K, times by that mode again, you end up getting another single value, and that is known as the modal stiffness, okay, Kr, for that specific mode. Now, to work out what Q is, we need to work out what the conversion factor is. And we've got this thing called phi. Okay, notice it's in square brackets, which means it's a matrix. And basically, you take all your mode shapes, okay, up to mode R or continuously, and you just put them next to each other in the matrix, okay? So obviously, if this is a 3 by 3 degree of freedom system, we'll have x1, x2, and x3, and we end up with 3 values here, 3 values here, 3 values here, and so you end up with a 3 by 3 matrix. And obviously this will grow in length as you go up in terms of degrees of freedom, okay? So R values, we'd have obviously an R by R matrix because we'd have R values in the mode shape. And so column R of the modal matrix is the modal vector for mode R, okay? So it's that mode shape, the rth mode shape, okay? With each element giving the amplitude of displacement in each coordinate for that mode, okay? So when you're exciting the system by that natural frequency, you get the mode shape, and each value in here will be the relative displacement. If this is 1, then all those will be relative to that displacement, but basically it's the amplitude of the motion, okay, in that mode. And so here we've got mass 1, mass 2, mass 3, and this is the mode, okay? So the first value in the suffix will be the specific mass you're talking about. The second value in the suffix will be the mode that you're talking about. Okay, so there's the starting 3 by 3. First suffix is the response coordinate number, so we're dealing with mass 1, mass 2, mass 3, and the second one is the mode number. And that forms our matrix phi. Now phi is important because that's the key to swapping between x and q. Okay? And it also has a special feature that if you take phi, you transpose it, you multiply it by your mass matrix and multiply again by phi, you end up with your MR terms. And then it's a diagonal matrix, all the other terms are 0, you've got your MR terms down there. And if you do the same thing with K, you just end up with a diagonal matrix with those KR terms. And so you can imagine that if you've got, again I'm going to try and write on the screen now. Let's go back. If you've got our mass matrix with M1, M2, M3, and every other term is 0, which is essentially what I've just said, those are my modal numbers, okay, this is a modal matrix. And then obviously I multiply this by Q1 double dot, Q2 double dot, and Q3 double dot. And then I've got my KR, which is basically K1, K2, and K3, and all the other terms are 0. This has the benefit that this equation, Q1, Q2, Q3, equals some force, okay? This has the benefit that each equation is uncoupled. If I take the first equation, I've got m1 times by q1 double dot plus k1 times by q1 equals f1. Suddenly, in terms of mode shapes, I've got this modal variable, and the equations are uncoupled. It doesn't involve q2 or q3 or so on, okay? Because these matrices are diagonal. Okay. So if I go back to the slides now. Now, so that's what I showed, okay? Because those matrices are diagonal, okay? If I take my MR, my KR, and I multiply by Q, okay, I get the equations of motion, and they're not coupled together. Now, often it's quite nice when you're doing this if you can scale this so that MR equals 1. Equals, basically each value of MR equals 1. And there's a way you can scale it such that you can employ this equation, okay? I won't go through the derivation of this equation, but basically you take your mode shape, you divide it by the square root of each value. So take the rth mode shape, you take your MR value that you found, divide it by the square root of that, and you get another vector. Okay, this is a vector, this is a vector. You take each value of that vector, divide it by the square root of MR, and you get another vector that's been scaled, such that if you take that vector, such that if we go back to that equation to find MR, okay, if you take that vector now, okay, if that was that U value instead of X, you'd end up getting 1 for MR. Okay, that's the whole point of that process. Okay, so it's still a mode shape. It's still a valid mode shape as well. Okay, it's just not scaled to 1. X1 won't necessarily be 1. It'll be a valid mode shape. The relative motion will still be the same. Okay, but you just won't have that value of 1 at the top. So you scale it. Okay, and you end up with there's our equation of motion that we had. And what you can do is to uncouple the equation, you take phi, you multiply. X is phi times by q. Okay, so if you say you took x and you divided by phi, you get q, or multiplied by phi inverse, you get q. Where q, like I said, is what's known as a modal coordinate. Okay, and so if we stick in, for every time we've found x, we stuck in phi times by q. Okay, and we've got therefore our m vector and our k vector. You can see we've already worked out what that is. Phi transpose times by m times by phi, we know is our mr term, and phi transpose times by k times by phi is our kr term. So we end up with mr times by q double dot times by plus kr times by q equals, obviously we pre-multiplied by the transpose, so you end up with your forcing function multiplied by the transpose of phi. And like I said, because MR and KR are diagonal matrices, they are therefore uncoupled. And so we've gone from a process where we had n number of coupled equations, which are a bastard to solve, okay? We've ended up with n number of uncoupled equations, which are all easy to solve. Okay. That's the beauty of modal analysis. And so, as I said, by scaling, you end up with MR being 1. This is I is identity matrix, where you have 1 down the diagonal, okay? And it just so happens that when you do the same process for the K, instead of 1 down here, you end up with all your natural frequencies, okay? So 1 times by Q double dot times by your natural frequencies times by Q equals your forcing function. Now that's very similar. Back in level 1, remember we had x double dot plus k upon m x equals 0, or force divided by m. Okay, this equation is what we've got here. Okay, because we said that for a single degree of freedom system, this could be solved so long as omega naught, your natural frequency, is root k upon m. Well, basically we've got the same thing. Q double dot, x double dot, okay, natural frequency times by displacement equals your force divided by m in that case. So you've got n number of uncoupled equations, which is what we're looking for. And like I said, the equation describes the equations of motion in terms of the modal coordinates. Okay, so we're not talking about x here, we're talking about modal coordinates. They're not coupled, each involves only one mode, okay? So we're not worried about what the other modes are doing, we're just dealing with one mode, okay? And will tell us how much that mode contributes to the overall response of the system, okay? Each having natural frequency omega r and being subjected to excitation defined by Fr, which will be a certain excitation. So that equation is quite nice and simple to solve, okay? We've done that before, back in chapter 2, okay? And depending on what f of t is, we've solved it for a number of different cases, a step function, a ramp function, a sinusoid stuff, which we did in chapter 3, if you remember, okay? The solution to the mode space equations are the responses of each individual mode, okay, a vibration expressed in terms of the modal coordinates q, and then you apply the modal matrix to q to convert it back to your x, which is your displacement. Which is that step there. Okay, once you've got the response, solutions for q, multiply it by phi, our modal matrix, and you get x back again. Okay, the response of the system at any instant is a weighted sum of all the different modes shapes, okay, which you know, and the modal coordinates qr define how much each mode shape contributes to the system's overall response. That's exactly what I said in the previous slide. So there's a step process. The first 3 steps we've done, okay? Find the equation of motion, using the MIM, find the natural frequencies, and find the mode shapes. Now, like I said, often you would use a computer program, like that I function in MATLAB, to find those things, okay? And in some of the questions that I've actually, that we've gone through, okay, I've actually given you things like, if you look at the end of the chapter, let's look at, for example, question 6, I've actually given you the natural frequencies, and I've not given you the mode shapes, but I've given you the modal masses, okay? And you'll see that there's variations on the theme, but basically, that's the process you go through. And for the 2-degree of freedom system, it's fine. 3, it becomes a bit more difficult, and 4, like I said, you wouldn't be expected to solve something like that by hand. Step 4, this is a new thing, is you find the modal mass and stiffness matrices, okay? Step 5 is you rescale that modal mass to get unity, okay? You then deal with the applied force. You then find the independent equations, so your q double dot equal plus omega squared times by q equals your applied force, okay? And then you solve that equation and you convert it back to your displacement. So there's 8 steps. The first 3 steps is old stuff. Equation of motion, so using the correct method, natural frequencies, mode shapes. Step 4, find the modal mass and stiffness matrices. So we're going to deal with that. Step 5, you rescale the modal mass to units, okay? And then you deal with the applied force. You find the independent equations, solve them, and then you convert back to your displacements. That's the process to go through. And each of the problems we're going to go through, we have that process.